Okay, now we're almost at the very end. So we had what the E1 and E2 are as far as their magnitudes are concerned. And we have EBX and EBY, which are just the sum of the electric fields in the X and the sum of the electric fields in the Y at our point of interest, which is defined as point B in space. And we're just going to go ahead and plug everything in and find the magnitude of the vector. So let's first write what the vector actually is. So the electric field at point B is the sum of the electric field in the x, I hat, plus the sum of the electric field in the y direction, j hat. So we already have what most of that is already. So let's go ahead and put that in. We see for the EX part, that's going to be K times Q1 divided by A squared times 2 divided by, also multiplied by radical 2 there, minus RE2, which is going to be K Q2 over 10 A squared times the square root of 10. And all of this is our I hat component. So might be better if we first decide to move this over here, right? And now we're going to deal with our y components, which will be k times q1 over 2a squared. Then put a radical 2 there, plus, this time, because the y components add, k q2 over 10a squared, square root of 10. All of this as j hat. And now we're going to notice that in this result there is a lot of stuff we could actually pull out of this. Most notably, we can pull out k divided by a 2a squared from everything. So let's just do this in simple steps first. So we get k over 2a squared here multiplied by q1 over the square root of 2 minus q2 divided by 5 times the square root of 10 I hat plus k times q over 2a squared multiplied by, oh wait, where did that q come from? q1 divided by the square root of 2 plus q2 divided by 5 times the square root of 10 j hat. Now this is not so bad because we know that the magnitude of our vector EB is going to be the magnitude of the sum of the vectors in the x component squared plus the sum of the vectors in the y for the electric field squared, square root, and that's it. So you'll notice that there's a common coefficient here in front of both of these vector components. And this is all part of the x component, and this is all part of the x component, the y component. So we can plug them in, and then you're going to see quickly, I'm just going to do this real fast, that you're going to get k over 2a squared multiplied by the square root, something very large, which is q1 over the square root of 2 minus q2 over 5 square root of 10 squared plus q1 over the square root of 2 plus q2 over 5 square root of 10 squared. Now that part we could do all the other messy algebra if needed. Now if I wanted to, I could try to make this even more simpler on myself. For example, if I go over here, I could just as well have opted to say, well, there's also a radical 2 I could have pulled out of all of this. So I could say my electric field vector is equal to k over 2a squared square root of 2 multiplied by q1 minus q2 over 5 radical, whoops, that should be 5 square root of 5 I hat plus k over 2a squared square root of 2 q1 plus q2 over 5 square root of 5, sorry, had a dumb moment there, j hat. And I could just as well work with this as well. And you'll see that, well, this is not too bad to find the magnitude of EB, that electric field vector. That's just going to be k over 2a squared square root of 2 multiplied by this ugly looking radical, which is q1 minus q2 over 5 square root of 5 squared plus q1 plus q2 over the 5 square root of 5 squared. So that's pretty simple to do. Now, what about the direction? We'll address that, I guess, in another video.